much. I'm so happy that you are here again. And again, this is Dr. Brad Layton with the Missoula College.
Morning, everyone.
And we are excited to get going today. This program is brought to you from the Montana World Affairs Council as well as the Dennis and Phyllis Washington Foundation. I'm just going to hand it over to you because we did the big introduction last week. And I know I'm excited to hear from some of the schools. I've heard from some of your teachers that you've been putting together some information for us on your homework. So I'm going to go ahead and turn it over.
Okay. Hey, good morning, everybody. And I'll also follow it up and thanks to Dennis and Phyllis Washington Foundation for helping make this happen. So I'm just going to get right into the talk. I'm going to follow up with a few answers to some questions that we left with last week, and then we'll see what kind of homework you all were able to come up with for this week. And then finally, by the end of this week's lecture, so this is lecture 2 of 3. By the end of this week's lecture, I'll give you a few more homework problems for week 3, and then we'll wrap it up. And I'm really excited this month. It's April. Also happens to be my birth month. I'm going to be 45 on the last day of the month, but it's Earth Month in some respects. Earth Day is on April 20th, so I don't know if there's things going on in your town. There's a lot of cool things going on in Missoula, so that's where we are with April. So let me just start with another quote. Last week I started with Kelvin, so read this, and before it pops up, raise your hand if you know who said this. Well, can I cover the bottom?
You can cover the bottom.
Well, anyway, you've probably heard this before, but Thomas Edison. Anybody not heard of Thomas Edison? Okay, so everyone by now. Inventor of the light bulb, inventor of thousands of different inventions. I was just reading about him a little bit last night, and one thing that he said he was really proud of, most of his inventions were, they were driven by profit, so he was out there to make some money off the things he built. But most of the things, his inventions were also relatively peaceful. The things that he invented were to make humanity's life easier rather than harder. So I didn't find any counterexamples. So I've received a lot of inspiration from Thomas Edison. In fact, my son's middle name is Edison. we have the same initials, B-E-L. So he's Blake, I'm Brad. But anyway, just enough about me. So April 15th, hopefully everyone filed their taxes. Everyone got their taxes in? Good, nice. Way to go, Gardner. Thank you. So what I wanted to start with were any results that the teams had. So it sounded from my conversations with Allison that some of the teams actually did little experiments. Who did their experiment to see how powerful you are as a person? Just raise your hand if you did something. Okay, I've got one student from Moore, several students from Moore. So Moore, did you do a group experiment, or did you each do it individually? Maybe a little bit of both.
We did a group.
Okay. Okay, great. Did you take a video of that? Because if you did, we can show it here. I've got a space for that in my lecture to show it.
Yeah, we did.
Okay. Well, if we can get that going later, maybe we will. Maybe you just put your computer up in front of your screen, and maybe we can even show that. It might be a little funky, but we can try it.
We can try it. And if they want to just tell us about it a little bit right now.
Oh, yeah. Just give me a quick rundown of what you did.
Well, some of us ran 20 meters, and we timed it by seconds, and then we took a bike, and then we pedaled for 20 meters, some of us. And then we...
Did you maybe lift weights or something? Because those are two pretty good ones, running or cycling.
We just ran and rode the bike.
Ran and rode the bike. What kind of numbers did you come up with for power in watts?
Well, I ran and I got 332.5 watts.
That's pretty reasonable. Yeah, nice.
That's some good power.
Yep. Did you use the kinetic energy equation?
I don't think we did. We used the different... Because we kind of got confused.
That's okay. Maybe what we can do for week 3, I'd love to see the results. You got the right number. Sometimes you can get the right number but get there the wrong way. But I'd love to, if we could just have you email me your equations, your numbers, because 233 watts sounds just in the right ballpark. And then maybe next week we can go over some of the math to just check to see how you got that.
Okay.
Okay, any other schools?
Joanne has something.
Oh, sure, go ahead.
You have the equation here, it's work equals force times distance.
Sure, work equals force times distance. That's a great place to start.
And then we
How did...
newtons, and Newton equals a mass times the distance divided by the seconds.
Okay. That sounds like a great place to start. Sometimes it's difficult to measure force. One force that we're always experiencing is the force of gravity, and that's our weight, and so we already know what that is. But a lot of times it's difficult to measure force when you're moving. Okay, anybody else? Stanford, Gardner? Okay, Gardner, what was your, how'd you do your experiment?
Okay, there's the microphone on in Francie. Can you read that?
I can read that.
Tell them what you did.
So we calculated her weight and changed it to kilograms, and then we used this. We used this equation right here, mass times gravity times. Where is it? Times distance and change in time. Wait, this is what? Right. Okay, and then this is the equation we used, and then we got 349.49 watts. Okay. And then to change that to horsepower, we divided by 7.46 watts, and we got 0.46 horsepower.
Wow,
and we measured 746 watts. Right. And then she did push-ups, and so we measured the distance from her shoulder up, and it was 64 centimeters, and it took her 1.5 seconds.
Okay.
Right there.
Okay.
Yeah. So
that's good. So, all right, and I think what we're seeing here is over a shorter amount of time, you can be more powerful. That's interesting.
Yeah.
That's a really good one, and maybe next week we can look at some of the math together. That looks like a great start and a pretty good ballpark. If you came up with something where I got 5 horsepower, then you probably know something is wrong. But if you're there in the 200 to 300 or 400 watt range, that's fantastic. Okay, any other schools want to throw one out there? It's okay if you don't have anything now. I can just get into the lecture because we have a lot to cover today.
How about Cupping? I'm having kind of a hard time seeing you today. If you guys want to, if you have a question or if you want to get our attention, just turn your microphone and talk to us because I'm having a hard time seeing the students this morning.
Yeah, we can see part of the screen, but not all of Cut Bank. Okay, well let's get into the lecture. Another bit of homework that I gave you was to look up the Kardashev limit, and we'll get to that later. We'll also talk a little bit about Jared Diamond because Kardashev and Diamond, whether they know it or not, are actually related. Okay, and then I did a little bit of homework because last week you all, I can't remember who asked the question, but somebody wanted to know what the most intriguing human-powered machine was, or the craziest human-powered machine was that I'd ever seen. I already showed you the Daedalus project, and I showed you the Decavitator project. Those were both MIT human-powered machines. But let's check out a couple more. So I've got, went to the YouTube, and this is a funny combination between, I think I've already downloaded here. This is a funny combination between rowing, which I'd shown you, and bicycling. Let's check this out. I gotta get my glasses on for this one. Whoa! Alright, so what these guys are doing, they're rowers, but obviously they're on a bike. They're on a tandem bicycle. One guy's pointing forward, he's called the captain. The guy in back is called the stillman. So this is where you train to be an Olympic rower if you don't have any flat water. I think they're in Crete right now. No, they made the video. So check it out. one for them is that there's very little drag. They're low to the ground. They're like a drag. They're going slower now, obviously, since they're going uphill. And it sounds like from some of the equations you went in, you could probably calculate how much power these guys are putting out. So here they go. They're still going up the hill. They're putting energy in the bank right now. Climbing the hill, they're overcoming gravitational energy. They're putting energy in the bank. Up and up the hill. And I'll guarantee this guy is probably 400 watts, maybe even 500 watts. Not sustainable for a lot of times, 400 or 500 watts. Much better music than before. Okay, so now they put all that energy in the bank, now it's coming back. You can see, they get some toast. There he goes. Okay, this is going to become an important concept later, is putting that energy in the bank. We'll stop that one. I've got one more for you too. So this is even a little bit crazier, but
world that burns black in their car anytime. We have built a human-powered vehicle
engineering drawing.
whereupon all 4 operators power the vehicle in concert like an engine. Based on automotive technology.
We're going about 60 miles an hour right now.
Hot rod. Steel tube space frame rail dragster to a 9 8 second. Hand built. Now, the FM4 human car prototype exists right now. And we have rocked it in Seattle.
All right. Okay, so those are the 2 videos that I found supremely inspiring because it's human power really being pushed to its limit, but also combined with technology. And that's really what's inspired me is combining humans with machines in ways like that. So this is another example of a bicycle. So in this case, you're mainly using your legs instead of your full body like you would be in rowing. But again, you can see that back-to-back tandem, very low drag, but double the power, right? You have 2 human powers running this, but only the drag of the wheels and very low drag because of the low profile of the bike. And you'd see this on airplanes, you'd see this on Formula 1 racing cars. Anything that needs to go fast is going to be low and light. So here's our own bike. These are University of Montana students. We had two gals and 5 guys on the team. They've graduated from the program and are out there working in the field, and some of them are still students. But this was us actually racing in Utah. It's kind of hard to see, but there actually are 2 seats. This is the captain's seat right here, and there's Evel Knievel sitting on it. No, actually, it's one of my students from Butte. And then there's the stoker's seat in the back. So again, that same back-to-back tandem is a super way to go fast on a bicycle. And then I had to show this one too. This is actually me pulling a log up the rattlesnake. So I showed you the bike park, but and you could run the energy and see. I was probably at 200 or 300 watts pedaling this up. This was a couple of years ago. Okay, so that's wrapping it up for human power. So let's get into the lecture today and talk a little bit about solar power. And I was going to play another audio, but I think it's tough for me to talk. And,
it might be hard.
So I was going to play Here Comes the Sun by the Beatles, but it turned out last week I played the 2 songs, and they got stuck in everyone's head, so I'll just not play any more songs this time. Okay, So today's lecture is primarily focused on solar power. Last week we were able to wrap our heads around that 2,500 calories. We turned that into 10 megajoules, and that was pretty easy to see. That's chemical energy. Now today we're going to talk about solar energy, and we're going to try to sort out exactly how solar energy plays a part in our lives every day, really. So I just pulled up a few examples. Right here we're looking at sunlight coming in through a window, and this is something that you use and probably take for granted a lot of times, unless the lights in your house don't work. But this is, allowing you to see around your house, not bump into things, not step on the cat, figure out where the fridge is, etc. Down here we have gardening going on. Obviously, if you didn't have the sun and the water for the garden, it wouldn't grow. I've got ranching and agriculture on the other side. So here's wheat growing, and here's an example of ranching. The farm animals are obviously eating the plants that have been grown by the sun. So hard to think of any example in your daily life where the sun does not play a role. So I mentioned daylighting. So let's just show a hand. So is sunlight related to heat? That's the next one on the list. Give me a show of hands if you think sunlight is related to heat. Okay, pretty obvious, right? So the sun shines in, hits something, that energy has to go somewhere, and it gets hot. In fact, I'm standing right here at the hive, and we're going to design a trom wall so that we can use sunlight to heat the building rather than having to turn on the gas, the electric all the time.
What is a trom wall?
Oh, so trom wall, it's just a big hot chunk of mass, really all it is. It's a way so everybody's probably put their hand on a hot road in the summertime, or a hot pavement. You've tried to walk across the parking lot.
How about a slide at the playground when you go down the slide in the hot sunshine?
Same thing. So it's just a big chunk of mass, except you've taken that slide or that chunk of road and pulled it into the building, and now you've got this nice hot piece of matter inside the building, and that re-radiates the energy into the building at night. So there's an example of sunlight turning into heat. Okay, next one. How is the sun related to wind, if at all? Who says that the wind actually comes from solar power? Okay, I got a couple of yeses up. How does that happen? Well, more or less what happens, the world is spinning. One side is hot, one side is cold, and you know that hot air rises. Anytime you've got a mass of hot air, that's going to rise. That can actually create winds that go in vertical loops. You'll also see it in valleys, in streams, and mountains, where that same wind, if you live on a mountainside, you probably know that the air sort of rises up the mountainside during the day, it comes back down during the night, and that's all driven by the sun. So the wind itself, you see these wind turbines out there spinning, that's actually driven by sunlight, believe it or not. Photosynthesis, pretty obvious, driven by sunlight. And I'm going to show you the molecule itself that takes that photon from the sun and turns it into chemical energy. What's the synthesis part in that mean? When you hear the word synthesis, what's it mean? It means you're making something. So what the plant is doing, it's making itself, in fact, it's sticking little carbon bonds together with the power of the sun, and I'll show you that shortly. Okay, how about wave energy? Is that coming from the sun? Who says wave energy comes from the sun? That's a tough one. That's a tough one. Well, it does indirectly because the waves come from wind. Wind blows across an ocean or a river, makes waves. So waves themselves, and there's a lot of energy technology that use waves for energy too. In fact, I'm working now with one of my students who works at the Belgian embassy in Washington, D.C. One of his countrymen is making a living now actually turning wave energy into electricity. They're in the process now of re-engineering a lot of the shorelines in Europe in the same way that the Dutch have been doing for centuries, because the seas are rising, and he's taking all that extra dirt and turning it into these energetic volcanoes in the ocean. Okay, how about tidal? Are the tides driven by the sun or not? Who says yes? I see one kind of
Who says no?
uncertain. Who says the tides are not driven by the sun? Yeah, this is a tough one. Well, it's yes and no. It's yes and no. So there is a little bit of solar tide. It's not from solar radiation hitting the planet. These are more driven by gravity. These are driven by gravitational differences between where the moon and the sun are in relation to the Earth. So in a sense, it's driven by the sun, but not by sunlight itself. That's kind of a tricky one. Okay, geothermal energy. And this is one that people don't think about, but in your lifetimes, I guarantee you, geothermal is going to be a major industry, especially in Montana. They're starting to crop up. We already have a bunch of holes in the ground from all the drilling. It gets hot when you go down deep into the ground. So geothermal, is that solar driven or not?
Thumbs up, thumbs down. What do you guys think?
Yeah, give me a hands up if you think geothermal is driven by the sun. We got one, again, one shaking. Well, it's, I'm going to have a hard time saying that it is, because mainly all that geothermal energy is left over from when the Earth was forming. The Earth was forming by colliding rocks together, very hot, uninhabitable place. So most of that geothermal energy is actually driven by ancient gravity. Some of it is still from fault lines. You've got a lot of friction underground. Anytime you have friction, you get heat. That's geothermal. So not really from sunlight. Okay, here's the next three. Coal, oil, natural gas. Who says those come from sunlight? Let's see a show of hands on that one. I got one very strong hand, another hesitant hand. Who says no on coal, oil, and natural gas from sunlight? Who says there's no way those came from the sun?
A couple of no's.
Okay, a couple of no's. Okay, a little controversial. So you might say, gosh, all that stuff's underground, coal, oil, natural gas, it's underground. How could the sunshine have put it there? Well, what we'll see is almost all of that, in fact, all of it, came from decaying plant matter, decaying organic matter. So all of those plants and animals we saw a second ago became buried underground. They got their energy from the sun. So it turns out that coal, oil, and natural gas ultimately did come from the sun as a result of photosynthesis. Kind of hard to believe. Didn't get there yesterday, got there a long time ago, and we're going to discuss that in Lecture 3. So keep that in mind. Those are really important. The coal, oil, natural gas didn't come from the sun just recently, but got put there a long time ago. Hydrogen from the sun? Okay, that's a really tough one. So as we know, the hydrogen is primarily, or the hydrogen's made from the sun. Who had breakfast for cereal this morning?
Yeah.
So if you remember from last week, I don't think we talked about it much last week, but the sun is made of hydrogen, and it's constantly taking those hydrogen atoms and crushing them together under the force of gravity. Those atoms become helium, and photons shoot out as a result of that energy. So the hydrogen itself is just left over from the beginning of the universe. It's still kicking around, and it's really the fuel for the sun. So it's one step above the sunlight that we're seeing. That's where the sunlight is actually coming from. Okay, how about biomass? Trees, grass, does that come from the sun? Let's show of hands. Yep. Obviously, sure, no problem on that one. The photoelectrics, so photoelectric energy, solar panels. Does the electricity coming from your solar panel come from the sun? Who says yes? Easy, okay. Is Stanford's sound on? I can't tell because I'm just seeing them looking but not really. Okay, good, okay. Stanford said, yeah, solar panel electricity does come from the sun. Lightning. Does lightning come from the sun? That's a tough one too. Indirectly it does. Lightning comes from static electricity, and that is all driven by water molecules rising up as they evaporate. So indirectly, lightning does come from the sun too. It's kind of wild. Hydroelectric energy, big thing in Montana. Northwestern Energy just bought the dams, right? Everybody knows. Does hydroelectric energy come from the sun? Show of hands. Stanford. Give me a yes if you think hydroelectric comes from the sun.
Oh, thumbs up or thumbs
All right,
down.
I got 2, 3, 1 has Give me a hands up if you think hydroelectricity does not come from the sun. I want to see that. Anybody? Okay. That's pretty obvious too. We just talked about it. The water from the lakes and rivers evaporates and ultimately comes back downhill. Hydroelectricity energy comes from the sun. Okay, and then finally fusion. That's the opposite of the fission reactors. Fusion is what's happening inside the sun. Two hydrogens come together, form helium. But once we get fusion energy going on the planet, that won't come directly. That'll just come from human ingenuity. Okay, so that's a lot to cover in just this one little slide. Sorry it's so boring, but as you can see, plenty of research to do if you're interested in this field. Okay, so here's where we're going to start a little bit of the math, and this is where I became very interested in this whole question of where our energy comes from. Ultimately, it does come from the sun, and I became very intrigued as an engineer to see, how can I contribute to this field mathematically, from a scientific and engineering standpoint. So I sat down. This was, finally published in 2008. You can see right above my head the year's 2008. I started writing this paper in 2004. So if you think your homework takes a long time, just become a professor and you'll realize it never really ends. So this is a paper that I wanted to write really with the intention of reaching a broader audience. Because a lot of times scientists, engineers, professors write these things and nobody can read it. It's just confusing because we spent so much time in school and we can only talk to each other. So I wanted to write this paper so that anybody could read it. My initial goal was to write it and sort of have it sitting there at the checkout at the grocery next to the Inquirer and Cosmo, and everyone sort of pick it up and say, oh yeah, I get it, I understand now. Well, I'm not sure my experiment worked because it's still not that easy to understand. This is a paper that I share with my freshman students every year, and it really kickstarts their interest in energy technology. So I thought I'd throw it out there. Let's just see if we can even check the title out. So the first one is comparison. You know what that is. And we did a little bit of that already. We've done a comparison of human power to horsepower. I heard of some push-up experiments. I heard of some running experiments, some cycling experiments. So really, in a lot of ways, a lot of science comes down to just comparing things. I think we know what energy is. Density, I'm sure you're learning about that in your high schools. It's pretty easy when you think about density in terms of lead is more dense than concrete, for example, or wood is less dense than water. But other things can have high or low energy densities as well. So let's think about this for one quick second. What has a higher energy density? A barrel of oil or a chunk of wood of the same size?
Let's ask the schools individually. Let's go to Moore. Moore,
Sure.
What do you think?
Moore, give me a hands up if you think the barrel of oil has a higher energy density than the same size log of wood.
Oil?
Oil? Okay, and then who says, okay, mostly oil. Who says wood at Moore? Okay, I've got one for wood. Okay. Stanford, let's get a vote for oil first. And then how about a vote for wood? Okay, the majority are saying oil here. And then Gardner, oil or wood more energy dense? Okay, oil. Anybody vote for wood?
Oh, it's the same.
No, I think it's just a little time delay. All right. Well, as it turns out, oil is more energy dense. In a lot of ways, that is what energy technologists are constantly competing with. So it's going to be easier in a lot of ways to ship somebody a nice dense barrel of oil than a chunk of wood where you're going to need much larger volumes to produce the same amount of energy. That's a challenge that we face in Montana right now. Anybody breathed smoke from a forest fire? Yeah, okay. It happens in the summer. If we could take that wood out of the forest now and then turn that into energy, wouldn't that be a better solution than having to go and fight fires and risk our lives all summer? So in fact, we're working on something like that right now. So hopefully that explains energy density to you. When we get down to this, what we'll see is, unfortunately, solar power is actually pretty puny and pretty wimpy. We compared horses and humans last week. Horse has much more energy density than a human, much more powerful. The same is true with solar versus almost all of these things. So we've spent several minutes now talking about how great and how powerful the sun is, but when it comes right down to it, the energy density, so if you have a cubic meter of photons, there's not much energy in there at all. As it turns out, there is only 1/4 as much energy in a box of photons as there is in a box of oil. So your homework for next week, and I'm just going to put it right up here, is go out there and tell me how many times this paper has been cited. I don't know the answer. I'll go look it up myself. But this is just a little bit of research for you to do. So what I'd like you to do is go out, and what I'm hoping your teachers can do is send me a couple emails on ways to figure out how to cite this paper. And there's a couple different ways to do it, and I can show you one way through the ISI, for the Institute for Scientific Information. And that'll just get you going and hopefully open your eyes to how much research is actually out there. So that's one homework for next time. Tell me how many times this paper has been cited in the last 7 years. Okay. Okay. Now we're going to get into the numbers.
Me. Are you talking about the paper, a different paper that we can't see the full screen?
Oh, I see. Yeah. So I will read it to you, or we can email it to you.
I will email the information of this paper to each of the teachers after the class today.
Perfect. And it's going to be pretty easy to find. If you go out there and even just Google Brad Layton 2008, the name of the journal is International Journal of Green Energy. I'll say that again. International Journal of Green Energy. You can go look for that. And if you're having trouble finding it, I'll even show you a little research tool so you can get in and dig into it a little bit. Okay, so as promised, we're gonna look at a few numbers, and these numbers, I'd like you to take a few notes. So, Cut Bank, did you all bring pencil paper this week? Thanks. Grab your notebooks. So write down that first assignment I gave you, and that was to figure out how many times that's been cited. Stanford, do you guys have pencil paper too? I see there's one student with a notepad. Okay. Are the three
really cut off? Okay. I'm actually going to take this and make this a little smaller.
Oh, okay.
Can everybody read that?
Yeah,
because
I think
I was hearing that the screen was...
Maybe it was getting cropped.
Is it easier with it large or small to see the words?
Larger, please.
We need a full screen.
Yeah.
Full screen. Okay. Thanks.
So it cuts it off.
So Gardner, can you read that top line? They don't have their mic on though.
You can give us a thumbs up or down too.
Okay. So the top line says that the total annual solar incidence, this is the light that hits the Earth, is 1.4 yoctajoules. So Stanford, I think there's one student there with a black coat on at Stanford. Can you write this number down? I'm not sure Stanford can hear us.
I think they can hear us.
Okay. Okay, so write down 1.4 yj, and then what you're going to write after that is equals 1.4 times 10 to the 24th joules. Okay, I think he's writing that down. Okay, so if you remember from last time, 10 megajoules was the daily human metabolic diet. So what I'm going to have you do is figure out how close we are to consuming the solar energy. So we already know that humans are living off of solar energy in one way or another. And what I'd like you to do is figure out how much of that we're actually putting to use. So 1.4 yoctojoules. Probably not a number you've seen or used too much in your daily life. Okay, now the next one, this is the incident solar radiation. This is how much power is actually coming to the planet in the form of solar energy 24/7, 365, all the time. 44 petawatts. So Stanford, write this one down too. 44 PW, and then write equals 44 times 10 to the 15th. So we know that 10 to the 3rd is kilo, 10 to the 6th is mega, 10 to the 9th is giga, and you've probably all talked about gigabytes on your memory sticks and whatnot. The next one coming, and I've seen these out there are hard drives that are terawatts, that's 10 to the 12th, terabits. Now we're talking petawatts, 10 to the 15th, so 1,000 times a tera. That's how much energy, that's how much power is reaching the Earth. That's how many joules per second are hitting planet Earth right now. Okay, now, this is, again, pretty funny to read, but this is only 1/10 of 1/100000th of the sun's total output. So, and the reason for that is the Earth is just one tiny little dot of all the potential dots that could be out there collecting energy from the sun. Kind of funny to think about, but I'll show you a slide, and I think you'll know what I mean by that in a little bit. So keep that in mind. How can it be that little? I mean, those are huge numbers, but it's still just a tiny fraction of the energy that's coming out of the sun. Okay, next thing I mentioned this before, the energy density of photons is actually pretty small. So the sun's radiation is one of the least accessible energy forms mentioned above. It's not easy to turn the sun's energy directly into electricity. It's taken us a long time to develop solar panels. It's taken a long time for us to develop wind turbines. We've been using natural gas, coal, and oil because they're kind of easy. You know, just, I don't know if anyone heard of the Beverly Hillbillies before, but good example of how easy it is to sometimes get to those older resources. Okay, and now here's the next one, and we're going to use this in a big way next week. So again, please write this number down. Human energy technologies convert chemical and nuclear energy. So again, chemical energy, what's that? Well, it's burning natural gas, it's burning coal, it's burning oil. Those are all chemicals. It's taking that chemical energy and turning it into thermal energy. Well, just making things hot. And I think if you go out and put your hand on a car engine, you'll understand that the chemical energy in the oil turns into thermal energy. So 16 TW. And again, what's the T mean there? Gardner, tell me what the T means there in that very last line. 16 TW. What does that mean?
Terawatt?
It means terawatts, exactly. So the big T means tera. That's 10 to the 12th. 10 to the 12th. Pretty easy to remember once you've discussed it a couple times. So write that down. Okay, now, who can tell me from last week's homework what the Kardashev limit is? Who looked up the Kardashev limit and has an answer for me? I see a couple.
I wonder if Cupbank does.
Yeah.
Oh, and we have. Oh, look at this. Here comes Gardner.
Okay, Gardner's
Scoot
fired.
over to a little bit there, a little more center.
All right.
There's a method.
Hold her steady. I think we can read it. A method for measuring civilization's level of technological advancement based on the amount of energy a civilization is able to utilize. Perfect. Okay, that's as good a definition as I've heard. Kardashev was a Russian scientist back in the 60s, and this is when the Soviet Union and the United States were having a space race. Who could launch something around the planet faster, who could get to the moon first, who could build the biggest nuclear, what have you. But Kardashev basically said humanity is using up energy at a greater and greater rate. At some point, we're going to use it at a rate greater than our star is providing it. So the Kardashev limit is the point at which a civilization, and thanks Gardner for pointing that out, a civilization is using energy faster than it's coming from its star. Now, is that possible? Is it possible to use energy faster than it's coming from the star?
Could we stop and just have a little discussion with some of the schools?
Yeah.
What do you guys think about that?
Let's start
down with Cutbank. Cutbank, what do you think about that idea?
I don't know, when we looked it up, we found the Kardashev scale, and it says that we haven't even reached level 1, and that means that we haven't even started using all of the resources available on our planet, so we haven't begun reaching out for energy or anything.
Okay, that's right. In fact, we've not reached a level 1 civilization yet.
We can waste
Good.
it.
All right.
Good.
How about, let's add some other things. Stanford, what do you think?
Yeah, we pretty much agree with Cutbank here. We haven't used anything really other than oil so far.
We would like to learn more about the Dyson sphere idea. It seems
The
pretty
Dyson
far off.
sphere. Okay, we can talk about the Dyson sphere. I think once you hit a Dyson sphere, you're in a Kardashev Type 2 society. Good.
How about more? Do you have any thoughts on this? Do you think it's possible to use up all of the energy from the sun? Our star?
We don't.
Because if we're not using solar power, panels. And
Okay.
But if we used
Maybe not possible.
and then we used,
But
so
if
if we
we
use solar,
constant-
wind, in addition to fossil fuels.
maybe not.
Oh, okay. So I can hear just a little conversation there saying if you're using solar energy plus fossil fuels plus all these others, maybe you could use more energy than is coming from the sun. Is that where you're going? Okay.
Yeah,
Okay.
let's just hear from more really quick. Do you have anything to add to the conversation?
Is Moore's microphone on?
Not yet.
Okay. Maybe Moore's microphone's not on. Go ahead and turn your microphone on, Moore, and let's hear. Is it possible for a civilization to use more energy than its star provides?
Maybe eventually, but not.
Maybe eventually. Okay. Yeah. Okay. So I think we're all in agreement. It sounds like we're not there yet. It might be possible if we get more aggressive with our energy consumption, but and maybe in the future somehow we'll get there. Okay. Good answers. Thanks for the engagement. Now, and the number I came up with is there were only 127 and 27 and 38. That's even a number, but 4 parts in 10,000, if you like, 4 parts in 10,000 of Kardashev Type 1 society, or Jared Diamond's photosynthetic ceiling. And if you haven't heard of Diamond before, well, first of all, let's take a look at what photosynthesis is. So when I first showed that slide of sunlight coming in through the window, I showed 2 people gardening, I showed wheat growing in the field. This funny-looking molecule, believe it or not, is the molecule that's taking that energy from the sun. It's taking little photons, squiggling their way down to planet Earth. Somewhere in this giant wad, there's a lone electron that says, "Hey, I'm just kind of hanging out on the periphery here." The photon smacks it, and now it becomes more or less a little photovoltaic panel right inside of that plant. So this is nature's photovoltaic panel. Everyone's seen a PV panel. Sometimes they're called solar systems, but they're the solar panels that you see on roofs or out in fields. This is nature's PV panel, and it does it one little photon and one little electron at a time, and this is what drives all of this photosynthesis. This is what we have. This is what we owe all of our carbon debt to. And next week, when we actually talk about Uncle Helios, we'll understand exactly where this energy is coming from. So this is photosynthesis at the molecular scale. We benefit from it at the human scale, at the civilization scale. Okay, but I wanted to show this slide, and just little takeaway: the Kardashev limit is the limit when a civilization uses all of the energy from its sun as fast as it's being put out. So you can imagine You could put this in banking terms, and let's say your parents are giving you an allowance, and as soon as they give you $5, you go and spend the $5. They give you 10, you go and spend the 10. They give you 20. There's really no banking anymore. There's no solar bank. We're using it as fast as it comes to us. We're not there yet. As I showed, we're only at 1/27,000th of that limit. But if you go back in time, we're approaching that limit. If you go far enough back in time, we were not using nearly as much energy 10 years ago, 20 years ago, 200,000 years ago, go as far as back as you want, as we are today. So we are still approaching that limit, and the question is, can we get there? Can we surpass it? And what are the implications? Okay, so that's the Kardashev limit. And I also wanted to show you a couple shots of Jared Diamond. Jared Diamond has written 3 books now. He talks a lot about the whole dairy. He spent a lot of time in Montana. He's a professor at UCLA, but I strongly recommend going and reading some of Jared Diamond's work. This guy has spent his time traveling the world. He's looked at collapsed civilizations. A lot of times, all we have left of former civilizations are some of the structures they built. A lot of times, these civilizations did not do enough planning and ended up collapsing because they were not as proficient as we are at predicting the future. He spent time on Easter Island. These people disappeared several hundred years ago. And in a lot of ways, one analogy that you can draw is really the Earth is just one big island. There's no, I mean, okay, we've been to the moon a little bit, we're trying to get to the star, but there's no life raft, if you will, to get off of this island. So he looked at civilizations that didn't really see beyond their borders well enough and collapsed because of how they overused their resources. I wrote the word pen pal up here because he and I have written back and forth a little bit. We share common interests. So that's something also. I saw at the beginning a couple of you students were talking back and forth. And that's the great thing about the internet now. You can really be connected with people across the planet who share common interests and passions. So look up Jared Diamond. Okay, so we've talked a little bit about science. We've talked about the sun. As you know, I'm a technologist. I'm an engineer. I am on the faculty at the University of Montana, and I work with the climate change folks. I work with the environmental science folks. I work with the geologists, the people that are out there sort of finding the problems. And then as a technologist, it's up to us to fix them, right? So we've been trying to fix them for decades now. We've built cars. We've built coal-fired power plants. We've built wind turbines. What's next? Well, one thing that I thought was a great contribution was to build a solar car. So this is a shot of my students and myself. This was from 2012. And what you see here are solar panels on the top. And we could do a little bit of math and figure this out, but it's not a whole lot of power. As I told you before, the direct photons coming from the sun are pretty wimpy. So there's not a whole heck of a lot of power. There's really only about 400 or 500 watts coming into this thing. And I saw that one of you was doing 300 watts with your push-ups. So this is a car that's small and lightweight that you can really just push by hand. We were able to go 15 miles an hour with it, and we were able, just as I said a second ago, we were able to spend that energy just about as quickly as it came in. So in a car like this, the energy comes in, and we were able to cross the finish line with more energy than we left the starting line with. Okay, so I think we're about to wrap it up. Let me just do 2 more little plugs, and then I'll be done.
Then do we need to talk about their homework for next week?
We'll talk about the homework. So here we are also competing with a different car. This summer, we've got the Energy Practicum. I would love to see some students come down to Missoula. We've got dual credit set up, so this is online if you'd like to come down to Missoula. It's a 2-week session, June 15th to 26th. So we'd love to see you down here. We also have stipends for teachers. So this is a National Science Foundation funded project. And so teachers, if you're interested in coming down, we have a stipend that you can come and participate and get credit. Okay, so we'll save that for next week. And then I just wanted to finish up and say thanks to the National Science Foundation. A lot of this is sponsored by NSF. We're actually streaming these videos to the National Science Foundation so that other schools can see it. We've had some help from the Perkins Foundation, from NASA, of course from the University of Montana, and then the Department of Labor has helped out too. Okay, so the homework for next week, write those numbers down, and what I'd like you to start thinking about is do your own calculation on how close we are to the Kardashev limit, and see if you can come up with a number for how much technological energy you consumed between now and next week. So we did human power last week. What I'd like you to come up with is how close you are to the Kardashev limit. So what fraction of the sun's power are you using yourself? But I want you to do it from a technological standpoint. How much energy is going through your house, through your car, through your phone, computer, etc. So you can then take into account your own technological consumption.
So do we want electrical, or do we also want chemical? Do we want...
Good question. Electrical, chemical. I'd like you to try to count for all of them. That'll be a good exercise. How much electrical, how much chemical, how much thermal perhaps. Probably you don't have a nuclear power plant in your backyard, so you won't have to count that. But go and look and see how much energy you consume in a week. It'll be a good little exercise.
All right, do we have any questions before we go? It's been a lot of information today.
Brain's full.
I know. Need a few minutes to digest.
Yeah. Can you hear me?
Yes.
Yes.
Okay, we weren't able to see some of the formulas that you had on your screen.
Oh, they got cut off.
Or can you get those somehow?
I will send those to you along with the title of Dr. Layton's article to look up for how many times it was cited in an email after the...
Right. We'll send the slides, and we'll also send the paper so that you're able to do some of the calculations that I've asked you to do for next week.
Okay, I have another question.
Okay.
What kind of units should we express this in?
Well, it would be great to just express units in joules. You can put the units in joules, it's probably the easiest. But if you want to work in calories, or if you want to work in BTUs, that's fine too. It's very easy just to convert it to joules. Everything that I've been talking about has been in joules, and that's just an easy way for me to think about it. And it's also a language that other scientists will discuss energy in. So joules would be best. But if you want to write them out in BTUs or calories or kilowatt hours, that's fine too. We can do the conversion to joules. Good question.
Wonderful. Anybody else?
Okay, thanks, Mark.
All right. Well, thank you guys. We look forward to seeing you next week and hearing your answers. And we have a really fun interactive problem for you to solve next week. So this week was heavy on the information. Next week is going to be heavy on you giving us some information. So it should be a lot of fun. We look forward to seeing you. And again, thank you to the Montana World Affairs Council and to the Dennis and Phyllis Washington Foundation.